Hello everyone, I am Xinyu from National University of Singapore, and today I'm going to present our work on the data efficient fine-tuning for the LLM-based recommendation. So today's presentation will contain 4 parts, and I'll begin with the background and motivation of our work. So we know that recent years have witnessed the great power of the LLM-based recommender system, and they have achieved exceptional performance in various recommendation tasks, including the CTR prediction, sequential recommendation, co-start recommendation, as well as the explainable recommendation. So in this work, we mainly focus on LLM-based generative recommendation, which has already been introduced by Juntao, I think the speaker's name, Juntao, so I'll skip that introduction part of the LLM-based generative recommendation. So to leverage the LLMs for the recommender system, we know that frequent fine-tuning is actually very necessary because of the 2 reasons. First of all, the LLMs are not particularly trained on recommendation data, so we need to fine-tune the LLMs to adapt the LLM from the pre-training tasks to the recommendation tasks. And the second reason is that recommendation data, different from other domains, the recommendation data is frequently updated every day. So, and we know that training the LLMs are very costly. So in this case, if we want to frequently fine-tune the LLMs for recommender system, it can be very time-consuming, and it can lead to high computational resource costs, which is quite infeasible for the real-world applications. So, we highlight that we need to make it efficient for the LLM fine-tuning. So the next question is how to make it efficient. Well, previous studies have already shown that the few-shot fine-tuning can have competitive performance compared to the traditional models. And from this figure, we can also see that with only hundreds of samples, the LLM-based methods can outperform the traditional methods that are trained on the full data. But existing work only explores the random sampling, and we think that this can lack sufficient representativeness to enable the LLMs to effectively comprehend the new items and the user behaviors. So we think the few-shot fine-tuning can be further improved by selecting the data that are helpful to the fine-tuning of the LLMs. So in this work, we propose the task of the data pruning for efficient LLM-based recommendation, which aims to identify the representative samples specifically for the LLMs. So a very related line of work of the data pruning is called the core set selection, and we roughly summarize them into 2 groups. The first is called the heuristic method, which typically assumes that the hard or diverse samples are quite important for the model's training, and they design different predefined metrics to measure the importance of the samples. For example, they might measure the errors between the prediction and the labels, or they might measure the gradient norm, where the value of the measurement, a larger value of the measurement indicate that the sample is more difficult. But this kind of work, of course, this is quite heuristic, right? And it makes sense, but it actually overlooked the impact on the overall performance. So the selected data from the heuristic method may be suboptimal. And to solve this problem, another line of work lies in the optimization-based method, which tries to optimize the selection of the subsets through some optimization problems, for example, the bi-level or the discrete optimization problem. Although it can have more accurate selected subset, it actually needs to solve the complex optimization problem. And this can be inapplicable to our case, to the large-scale recommendation datasets or the large-scale large language models. And another problem is for both of these 2 kinds of methods, they all need to rely on a model that is well-trained on the full data, which means that if we want to prune the data from these 2 methods, we need to first train the LLM first on the full data, and then prune the data based on the well-trained model. So this is also infeasible in our case because of the high training cost of the LLMs. So based on the above insights, we consider two objectives for the data pruning for the LLM-based recommendation. So the first one is the high accuracy, which aims to select the samples that can lead to higher performance. And another one is the high efficiency, which tries to emphasize the low cost of the data pruning process itself. And to achieve the high accuracy, I think the key lies in the ability to measure the influence of removing a sample during the training. So, for example, if we remove a user sequence in the training process, and then we test outcome performance, and we find that the overall loss increases. So, in this case, we can think that, okay, this sample is quite important because if we lose it in the training data, then the loss will increase. So actually, this is the data that we want to keep in the training data for the LLM. And to achieve the efficiency, a possible solution is to train a surrogate model, a much smaller surrogate model, for example, a traditional sequential recommender model, SUSREC, for the data pruning process. But however, to achieve these are not very trivial. For example, for the influence measurement, the most straightforward way is to apply the lean one out retraining, which means that for each time we remove a sample during the training process and then test the outcome performance. This is the most straightforward one, but it is very costly, even for a small model, because we need to retrain for many times. And for the efficiency, for the surrogate model part, it actually suffers from the gap between the LLMs and the surrogate models, which means that the selected samples from the surrogate models might be different from the LLMs because of the different learning ability. So to elaborate, for example, with the help of the rich knowledge encoded in the LLMs, some user behaviors might be more easy for the LLMs to capture. But meanwhile, the surrogate model might struggle to learn. So we think that it is also important to bridge this gap. So to this end, we proposed our method called DREC, which is a data pruning method to efficiently identify the influential samples for the LLM-based recommender. And we introduced two scores to achieve both accuracy and efficiency. The first, we introduced the influence score to efficiently measure the influence of removing a sample during the training process. And we also introduced an effort score to bridge the gap between the surrogate model and the LLMs. So this is the overview of our method. Specifically, it starts from here. So given all the training samples from the dataset, we first train a surrogate model on this full data. And then, based on the well-trained surrogate model and the full data, we will calculate the influence score. And at the same time, we use this full data, and with the help of the LLMs, we will calculate the effort score. And then finally, we combine these two scores to obtain the final influential samples. So in the following, I will introduce the two scores in details respectively. So for the influence score, the aim is to measure the influence of removing the sample during the training on the overall loss change. So to achieve this, we actually extend the influence function, which can be derived to measure the influence on the parameter change. And based on this, we can derive the influence of a sample on the sample loss, where the z here is the removed sample during the training process, and the z-test is an arbitrary sample for the test. So based on the equation 5, we can further derive the influence of removing a sample on the overall loss by replacing the z-test by the full training dataset D. So to wrap up, for the influence score for each user sequence, we can calculate the influence score based on the equation 6. Next, we look into the effort score, which aims to select the significant samples for the LLMs to bridge the learning ability gap. So here is the definition of the effort score, which is the gradient magnitude of the sample loss with respect to the parameters of the LLMs. And intuitively, this effort score essentially measures the learning effort of the LLMs to fit a specific sample. And if we visualize the average score for both LLMs and the surrogate model, we can find that indeed for the surrogate model and the LLMs, the gradient magnitude is indeed different on the same specific users. So to summarize our method, for each sample, we can obtain the overall score based on both the influence score and the effort score. So, and then based on the final scores, we apply the coverage-enhanced sample selection, which first clusters the samples and then use the stratified sampling, that is to try to cover the data distribution as much as possible. So next, for the experiment, for the empirical study, we evaluate the methods by selecting 1,024 samples on 3 data sets and on 2 different backend LLM-based recommender models. And this table shows the performance comparison between our method, DIRAC, and other coset selection baseline, as well as the random sampling. And we can find that our proposed methods consistently has the best performance on the 2 backend models and across 3 different data sets, showing the effectiveness of our method. And besides, we also compare our method with the same backend LLM model that is trained over the full data. And we can find that compared to the full training, we use only 2% of the data to achieve comparable or even better accuracy with less than 5% of the full training time. And that significantly reduced the training cost of the LLMs. And besides, we also evaluate the robustness on different surrogate models, and we can see that our proposed method with 3 different surrogate models constantly outperform the back-end Big Rec, which is the LLM-based recommender, under the full fine-tuning setting. Yeah, so for other in-depth analysis, we also have some observations. So for the ablation study, we can validate the effectiveness of each component of our proposed method, including the influence score, the effort score, as well as the coverage-enhanced sampling strategy. And then we also analyze the trade-off between the efficiency and the accuracy by varying the selection ratio from 0.2% to 4%. And from the results, we think that selecting 2% of the data strikes the best balance between the accuracy and the efficiency. And we also conduct the user group evaluation where the users are grouped based on the difficulty. And specifically, we use the loss value to group the users. And we can find that DIRAC actually improves the performance across each group. So it does not only improve the overall performance, but also improve the different levels of difficulties of the users. Yeah, so a quick conclusion of our work. The main contributions are twofold. So first of all, we propose the task of data pruning for efficient LLM-based recommender systems. And second, we propose a novel data pruning method that can efficiently and accurately identify the influential samples. So for the future work, we think that we can extend our method to more LLM-based recommender models and also some other data sets, including some cross-domain data set. And also we think that selecting pruning the samples from the item-wise is also worth exploring, because in our work, we now only prune the data from the user-wise. So each user sequence is a sample, but for each user sequence, we can also identify some influential items in the historical interactions to further reduce the cost of the training. And third, it is also important to enhance the inference efficiency, which has also been discussed in the previous QA process. Yeah, so I think that's all for my presentation, and thanks for listening. I'm happy to take any questions. Okay, thank you.